Hey everyone. Okay, let's talk about Lagrange error bound. So by this point, you should be real comfortable with Taylor polynomials, and you should know that Taylor polynomials are used to approximate functional values, just like linear approximations work. Taylor polynomials are much more accurate and are used to approximate various types of functions. So let's talk about that for a moment and then what an error bound is. Okay, so here we have the function that we would like to approximate. We cannot find the functional value for whatever reason, doesn't matter now, but we're going to use our Taylor approximation to go ahead and find a value at x, or at least an approximate value at x. Now, this is the actual function at x. So this is going to be x comma f of x. And this value is the approximation from your Taylor polynomial. So that is going to be x comma p of x. The distance between the two of them is the error, the mistake, how close you are. So we're going to call that our error. And we don't know what that error is, and we will never. But with Lagrange error bound, we can actually find the largest it can be. So you're off by no more than this much, and that's what the Lagrange error bound is. So let's write it down in this way. Let's say that the Lagrange error bound is the maximum possible size of the error, for lack of a better word. So the maximum error you can make is the Lagrange error bound. And it tells you that it can be anywhere between the functional value exact and the functional error plus or minus this error bound. Okay? So let's go ahead and let's look at it. Okay, here's the Lagrange error bound calculation. Now, you do have to be able to do this, and no, you will not be given it, but it's not that bad. And let me show you why. If you have a Taylor polynomial, I'm just going to write down the general Taylor polynomial term. That's going to be the nth derivative of the function at x times x minus c to the nth power all over n factorial. Now, if you look at the error bound calculation, all the parts are the same for n plus 1. So this is basically, I think we called it the neglected term. In other words, the term after where you stopped. So this is the next term, the n plus first term. And if you look at it, all it is, let's point some things out. Actually, let me just underline some things. Here is the n plus first derivative, which we're going to talk about in a second. Here is x minus c of the next term. And here is n plus 1 factorial, the denominator of that next term. So these two pieces remain the same. They're right there, only you're going to the next term. This guy is being multiplied by it. Now, what is this guy? This is the next derivative, but it's not with an x inside. It is with a number z inside. Now, what is z? Z is the value, the number, in the interval c to x. Let me just fix that. That will make this the greatest, the largest. So that's why they call it the max. The value in between c and x that will make the derivative a maximum size. Okay, so how do you find that? Well, there are going to be three ways. First way is basically they'll give you a graph and it's fine. There's a clear bound for the interval and you can just read it. Second way is if it's a sine or a cosine, you know it's not going to be any bigger or less than 1, and you should be able to figure out what value just by looking at it in that interval, which one's going to be the biggest. The College Board, and this is really important, expects you to and allows you to use a value of 1, even though it may not be the actual. Because the sine and the cosine max out at 1, it allows you to use that. They allow you to use that. So you're going to use 1 for the College Board. College professors, it's anybody's guess. Now, they'll also give you perhaps the maximum value, or you could infer it from the function. For example, e to the x, it's going to be the largest x value on that interval, and you can just use that that quantity. So we'll see it as we go when we take a look at these things. Okay, so now let's go ahead and put this to work and see how we do. All right, so this may be a little confusing to read, but basically they're giving you all the information to kind of distill it down to the really super important pieces for the error bound, and I'm going to do that for you too. So let's go ahead and write down what we would need for this. We're going to need, this is the 4th degree Maclaurin. That tells us that c is equal to 0. It wants us to approximate the cosine of 0.2. So that means that x is equal to 0.2. Now we're going to need the n plus 1 derivative, which is the f of 5, f prime 5. And that is going to be equal to the negative sine of x. So I just did that by for you. It's just you would start at the cosine, derive the cosine minus the sine, minus the sines, minus the cosine, so etc. and so forth. And you would go down five derivatives like we did when we were doing Taylor's. But this is the information you need. So let's go ahead and find our error bound. Let's write our r of x. So we're using r sub 4 of x, and that's going to be less than or equal to the absolute value of, now it's going to be x minus c to the 5th power. So that's going to be x minus c to the 5th power over 5 factorial, which is 4 because we have the 4th degree, but we're going n plus 1. And that is going to be times the 5th derivative, negative sine of z. So let's just go ahead and fill in the blanks here. So we're going to have x minus c is x minus 0, and x is 0.2. So we're going to have 0.2 to the 5th power. On the bottom, 5 factorial is a 120. Now all we have to do is multiply by the negative sine of z, and we're going to figure out what z is. Okay, so on our interval, we know that z has got to be somewhere in between our c value and our x value. So that means it should be in between 0 and 0.2. But the College Board has said, don't worry about it. Anytime you see a sine or a cosine, just make z equal to 1. So we're just going to go ahead and make negative sine 1. Okay, now we can finish and find our error bound. So it's going to be the absolute value of 0.2 to the 5th over 120, and we're just multiplying it by 1, don't have to worry about it. And that means that it's going to be less than or equal to, and the number is 2.6667 times 10 to the negative 6. So there is your error bound. That's r sub 4 at 0.2. Okay, so we know that's going to be the farthest away we can get from the actual functional value. Just for information's sake, if you were to take the cosine of 0.2 and subtract p sub 4 of 0.2, your Taylor approximation, that number is, let me see, I did it, it's point, oh my god, it's like times 10 to the negative 8th or something like 0.0000000888254. So you're basically pretty close to 1/1000th away from the actual value. It's an incredibly accurate tool, Taylor polynomials. Okay, so now let's go ahead and do another type of problem. This says use a third degree Taylor polynomial on the interval from 0 to 1 for e to the x, centered about x is equal to 0 to approximate e to the first. So we know what e is, and this problem is just meant to kind of show you with a familiar number how close Taylor can come with just even a third degree polynomial. So let's go ahead and start filling in some information we're going to need. So e to the first is what we're trying to approximate. We're pretending we can't figure out this number, I guess. So that's going to be 2.718281828. That's your number e. We're going to need to remember that e to the 0 is equal to 1, and that any derivative of e to the x is going to be e to the x. So we don't have to go ahead and find 4 derivatives here. Okay, so now let's go ahead and put this stuff off to the side. And let's go ahead and find r sub 3. Okay, so r sub 3 of x is going to be less than or equal to the absolute value of x minus c to the n plus 1 all over n plus 1 factorial times f to the n plus 1 derivative of z, and that's going to be max. I put max in the bottom. I don't like putting it in big letters out front. So our only job, we have all the information we need, is going to be to find the value of z that makes it a maximum. So let's go ahead and see if we can't figure what that is out. Okay, so what numbers are we allowed to choose from? What can z be? Well, the interval is from 0 to 1. So we know that z can be in between 0 and 1. Now, our derivative, our fifth derivative, f to the fifth of e to the x, is equal to e to the x. So you can probably see that the largest value that you're allowed to use is 1, and you can go ahead and use that. So it's just going to be e to the first. So that our z value is going to be 1. Now we can go ahead and use that. So let's fill in the blanks. So we're going to have x minus c to the n plus 1. So that's going to be 1 minus 0 to the fifth, to the fourth, over 4 factorial, and that's going to be times e to the first. So let's clean it up a little bit more. And that's going to be 1 to the fourth. We'll just call that 1. 4 factorial is 24. And then we're just going to have times e. Oh, and I just caught myself in a quick mistake. I put down f to the fifth up here where we're taking the fourth derivative. I was thinking about the last one. Okay, and I think it would still e to the x, so no harm, no foul. Okay, so our r sub x, r sub 3 to the x, our error bound, is going to be less than or equal to 0.1132617411326174174. 29. That's as far out as I use an Inspire, so that's as far as my calculator went. So there's your Lagrange error bound. That's the farthest distance away you're going to be. So if you want to use that to estimate 1, r sub x of 1 is going to be equal to Oh, I'm sorry. I meant the Taylor polynomial we have to use. Third degree Taylor polynomial is going to be p sub 3 of x is going to be equal to 1, or I should say just, yep, e to the, this is our 0, 1 over 0 factorial, plus 1 over 1 factorial, plus 1 squared over 2 factorial, plus 1 cubed over 3 factorial. And that's going to be equal to 2.66667. And E is 2.71828. And we are off by about 0.05161, which is less than the actual error of 0.11326. So does just a fine job there. All right, let's see, we have one more problem to do. This should be a 1, because we're estimating 1, and that's what we did. Okay, now let's spend some time on this. Okay, so a typical question you'll see is, what's the smallest order? What's the least amount of terms you need to use for a Taylor polynomial centered at x is equal to 1 that's going to approximate e to the x minus 1? All right, so it's on this interval. So there's your c and your x. Let's go ahead and see what we need here. I like to write down all my information. So c is going to be equal to 1. That's where it's centered. You know it's on the interval 0 to 3. We know that f of x is equal to e to the x minus 1. And f to the 4th power, it's going to be the smallest order, f to the nth power of e, any derivative of e to the x minus 1 is going to be e to the x minus 1. It's going to be a chain rule, but then the derivative of x minus 1 is just going to be 1. So all the derivatives are going to be e to the x minus 1. They do that on purpose. I think you'll find that it's not going to be very tedious on tests either. Okay, so let's go ahead and take a look at this. All right, r sub 3 of x has to be less than x minus c to the 4th. So we are centered at x is equal to 1. So we've got, we're going to have f to the n plus 1, the maximum that we can get, times, this is all an absolute value, x minus 1, because we're centered at 1, so x minus c, over n plus 1 factorial, and that'll do that. And now we just have to find our z term. So z is going to be equal to 1 to 3. It's going to be in between 1 and 3. Now, just using that, we know that 3 is going to be our number because that's going to give us the largest possible value. So we know that z, the z we're going to choose, is 3. So let's go ahead and fill in some more. Less than or equal to e to the 3 minus 1 times 3 minus 1 to the n plus 1 over n plus 1 factorial. And there we have it. Now this has to be less than 1 because that's what the question states. So that's why I set that less than 1. Now the other thing is I don't think I mentioned was that was that 3 here also came from that interval 0 to 3. We're using we're finding the error bound as if we were to use 3. So that's where that 3 came from, and that came from our calculation of z as well. Okay, so let's go ahead and take a look and see if we can clean it up just a little bit more before we start messing with the algebra. So we're going to have the absolute value of e squared times 2 to the n plus 1 over n plus 1 factorial. That has to be less than 1. So what you're going to do is you are going to go ahead and plug this into y equals. Let me get a little bit of room here for you. And when you do that, you're going to get a table of values. And if you notice, we've got to be less than 1 there. So the first time it's going to be less than 1 is at 5. So we're going to need a 5th order, 5th degree Taylor polynomial to do that. So let me go ahead and see how I could write that kind of nicely. I think I would probably write something like r sub 5 of x is less than 1. Yeah, I mean, that's basically, I would write it, and that's basically 5th order. Answer the question. And that's that problem, guys. All right, that's it. Hope everything's good with this. It's not too bad. A little bit of practice, and you'll be just fine. Have a good one.